so let's say okay. Now, from what we did in the previous midterm 1 or midterm 2, by induction we were able to prove that this thing right here, 1 plus 2 plus 3 all the way up to n, equals n times n plus 1 divided by 2. Okay. Well, what's another way to write that is that would be n squared divided by 2 plus then n divided by 2. Sorry, guys, let's do big theta. I'm going to do big O and big omega. Well, let's do big theta through big omega and big O. Okay. Well, the first one, you'd say, well, no, this thing, well, it would always be less, bigger than n squared divided by 2 if n is going to be a positive number. N has to be a positive number because we're going 1 plus 2 plus 3 plus 4 all the way up to n. Okay. Now, looking at this the other way, n squared divided by 2 plus n divided by 2 would be less than or equal to n squared divided by 2 and then plus n squared divided by 2, which would just equal n squared. Okay? And so what is the meaning of all of this right here? Is that n squared divided by 2 is going to be less than or equal to 1 plus 2 plus 3 plus dot 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 all the way up until n, which is going to be bounded by n squared. So let's isolate these two things right here. So, A is going to equal 1/2, and B is going to equal 1. And of course, you need to prove induction before doing this, but we've already done that. So, okay, so let's look at some other things which are not polynomials. Let's consider exponentials. Let's say, okay, let's take another type of object that we're going to deal with. And so instead of talking about some type of finite sum, let's say how are we going to show that n factorial is big O of n to the nth power? Okay. Well, let's look back at our definition of what we want to see with big O. Okay, so for big O, we want it to be bigger than 0. Well, fine. Okay, and we want this to be bounded from above by big O of n to the n. Well, n is greater than 1. N is greater than 2. N is greater than 3. N is greater than 4. All the way up until n. N to the nth power. Okay, so those aren't too bad. Dealing with polynomials, I mean, the main thing is that you have to have the leading coefficient be greater than 0, so it doesn't have tend towards negative infinity. With dealing with n factorials, I mean, n is greater than 1, n is greater than 2, all the way up until n. That seems a little obvious. Let's look at one that is not as obvious. Okay? So, sometimes there are problems that are very special ones. And these very special problems have some unique traits in them. Okay? And so, one of the special problems that we deal with that is directly related to discrete math is the harmonic series. Now the harmonic series will be the sum k, which equals 1 to n of 1 divided by k, which would equal 1 plus 1 divided by 2 plus 1 divided by 3 plus dot, 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 all the way up to 1 divided by n. Okay, so some of the ones we were doing a second ago, we could get with some basic inequalities to prove it. Now, showing that the harmonic series is big theta of the natural logarithm, that's not like openly obvious at this point. And how will we prove something like that? Well, this actually correlates back to something that I talked to y'all about at the very beginning of the semester, which is the relationship between series and integrals, okay? So way back at the beginning of the semester, we were talking about if and then statements. So if a function is differentiable, then it is continuous. Just because it's continuous does not mean it's differentiable. But one of the early things that I showed y'all was one of the if and only if statements, okay? And it said that if you have an infinite series that corresponds to a continuous function, well, if the integral converges, the series converges. If the integral diverges, the series diverges. It's an if and only if statement, okay? We're going to use that same type of concept to try to investigate this problem right here. Okay. So, how can we come up with a relationship between this 1 plus 1/2 plus 1/3 all the way up to 1 divided by n and the concept of this big theta notation? Okay. And remember, when we talk about big theta notation, we're talking about it being bounded from above and bounded from below. And when you do the integrals in the series for the Riemann sums, you're getting the boundary above and below. Okay, so this might seem like some type of arbitrary notation that is just thrown out there for no good reason. No, there's good reasons within logical arguments to actually do this. So what we're gonna do right now is we're gonna go over the Riemann sum of this thing. Okay, so if I did the function, let's say, okay, so now the integral from 1 to n of 1 divided by x with respect to x. And I know some of y'all haven't had calculus, but what I'm doing right now is I'm just calculating the area under the curve. This would actually equal the natural log of x evaluated at 1 and n, which would equal the natural log of n minus the natural log of 1. And the natural log of 1 is 0, so this equals the natural log of n. Okay, so the area under the curve, f of x, which equals 1 divided by x, is equal to the natural log of n. Right, and once again, this is, I've talked about it from the beginning of the semester. There's an interplay between the continuous and the discrete. So how could we actually investigate the harmonic series and compare it to this continuous integral? That becomes the question. Okay. Actually, my students' extra credit project for Calculus 1 is Riemann Sum, so they'll be turning those in hopefully this week. Okay, so we're going to look at a left sum and a right sum of this thing. Okay, so what if I rewrote this in a slightly different way? Okay, so I've got my f of x, which is 1 over x. I'm going to leave it so you can see it right there. I'm going to take that same f of x it's going to go all the way off until n, and I'm going to put, oh, sorry, off the screen, n minus 1. And I know this is not the scale, but I got to fit it onto the screen. So, okay. There's a dot, dot, dot. Okay. Now, what would be the height of this first term would be 1. That would be 1/2, 1/3, 1/4, and so I got all the way out to this term, which would be, the height of it would be 1 divided by n minus 1. Okay, now on the previous one we said, okay, the integral of this thing is equal to the area under that curve, which is equal to the natural log of n, okay? Now, if you think about these rectangles right here, Between 1 and 2, the base of the rectangles is just going to be 1. The height of that first one is going to be 1. Between 2 and 3, the base is going to have a length of 1. But its height is 1/2. And if you look at these rectangles, every single one of these rectangles lies above the curve. Okay? So when making a comparison here, what can we say about this? Is that the natural log of n is going to have to be less than 1 plus 1/2 plus 1 divided by 3 all the way up until we get to 1 divided by n minus 1. Okay? Because all of those rectangles lie above the graph. Okay, well, if I can make this statement right here, there's nothing for me to stop me from adding in the extra term. Okay? All right, fine. So the natural log of n would be less than or equal to 1 plus 1/2 plus dot 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 plus 1 divided by n minus 1. And if I feel like adding that extra term in there, because I'm trying to investigate the harmonic series, so I want all my inequalities to match up. If I add in an extra 1 over n, yeah, it's still bigger. 1 over n is a positive number, so screw it, add that extra 1 in. So, what do we have right now? The natural log of n past 3 is always going to be positive. Okay? So, what type of notation are we looking at right here? We're basically saying that the harmonic series is big O of the natural log of n. Okay? Fine. But what is the next condition that we need? We need that the harmonic series is big omega of natural log of n. Okay, so we're going to try to find a way to make natural log of n be greater than the harmonic series itself. Now, this is the difference between the comparison of left sums and right sums, and is it the justification for the integral rules in infinite series? Okay, this is just a very specific case of this. Okay, so if I take my same graph Okay. Now, when comparing these two things, we're comparing a left sum and a right sum. Now, this is going to be a right sum, meaning we're using the right endpoints to calculate this thing. And all of these are going to be below the graph. Okay? And one of the caveats for doing something like this is that the only way to use this comparison of left sums and right sums is if you have a positive decreasing function. Okay? Normally in calculus books it says positive continuous decreasing function. Continuity can actually be thrown out of that. I had an interesting lesson in graduate school when I created a test that had a couple of correct answers on it, and it was pointed out to me afterwards. Because in analysis you can throw away continuity. Well, the sum of this thing is going to be all of the rectangles are going to be below the graph. Okay? So since all of these rectangles are below the graph, the area of these rectangles is going to be less than the actual area under the graph because we have this extra gapping area on each one. So this one was above the graph because of this extra gapping area that is coming from using the left sum. Now this sum is going to be less than the graph because of this lacking area along each one of these. So what is that telling me? That's telling me that 1/2 plus 1/3 plus 1/4 plus all the way off to 1 divided by n, all of this is going to be less than or equal to the natural log of n. Okay. Now, when doing this type of left sum and right sum, having this big theta notation, because these things are not equal, they're creating boundaries from them, you always end up with these slight discrepancies. Like the integral does not equal the infinite series does not equal the integral, but they're both bounded by each other, and so they're big theta notation if you want to think so, but there's always this discrepancy of like they don't exactly match up right, okay? And so the way they don't exactly match up right, when I'm comparing this one right here, what is the term that I'm missing? I'm missing this 1 divided by n, okay? But since this is a greater than or equal to inequality, this is coming directly from the graph, okay? And then I can say, sure, fine. I can add on a 1 over n. It's going to make it more positive. No big deal. Okay, now what's missing on the graph of this one is the initial term of 1. We don't have that 1 inside of it. We got to think about how can we add on an extra 1 to this problem, okay? Well, let me see. I've got another inequality that says that 1 is going to be smaller than the natural log of n when n is greater than or equal to 3. Okay, now why am I saying n is greater than or equal to 3? Because n would have to be greater than e to the 1. Okay, so when you look at this thing right here, n just has to be greater than or equal to e. Okay, and e is around 2.7, so we just say, all right, if n is bigger than 3, then the natural log of n is going to be greater than or equal to 1. Okay. And so what I'm going to say, I'm going to add these inequalities. And I get that 1 plus 1/2 plus 1/3 plus all the way off to 1 divided by n. And so I'm adding in the 1 into that statement, and I'm adding in the natural log of n to the opposite side. It's going to be 2 times the natural log of n. Now, sometimes in calculus when I'm teaching this, I make kind of a hand-waving argument because there's a missing term at the beginning and then there's an arbitrary a sub n at the end, and then I just let that go to infinity and it goes to 0. But since we're talking about finite case in this class in discrete math, we're actually going to make the comparison. And so how do we justify our big theta notation is that we have our first statement, first inequality that is occurring right here that I got from doing the left sums, and I just added in an extra term, okay? And then I investigated my right sums, And well, what was missing from it was the original 1. And so I had to say, well, okay, I gotta add this in somehow. And I know that the natural log of n is greater than 1 after a certain term, so I can add both of those to create this inequality. Create an inequality. Now we can combine these inequalities. So the combination of these inequalities is that the natural log of n is going to be less than or equal to 1 plus 1/2 plus 1/3 plus all the way off to 1 divided by n, which is going to be less than or equal to 2 times the natural log of n. Okay, if we just want to clean that up a little bit, we can say that the natural log of n is going to be less than or equal to the sum k, which equals 1 to n of 1 divided by k, which is going to be less than or equal to 2 multiplied by the natural log of n. Okay. So the sum k, which equals 1 to n of 1 divided by k, is big theta of the natural log of n. Okay. And now some people, in this case, you would say, oh, does this mean that the harmonic series is bounded? No. As n tends towards infinity, this whole thing tends towards infinity. This is asking more of the questions of how fast is this thing moving towards infinity, okay? And the harmonic series is a very special series in the sense that it is going towards infinity at like one of the slowest possible rates that you can go towards infinity. Think about exponential growth just goes way up really, really fast. Logarithmic growth is very, very slow. As it tends towards infinity, it does tend towards infinity, but logarithmic growth, remember when we talk about logarithms take things that are on very large scales and they bring them down to smaller ones. Those scales can become infinitely large, yes, but the growth of logarithms itself is very, very slow. So the harmonic series is the one series that it tends towards infinity, but it tends towards infinity in the slowest possible way. And as an example, this like how slowly does the harmonic series tend towards infinity? Okay, the harmonic series actually serves as a boundary. If I said the sum k, which equals 1 to infinity, of 1 divided by k to the 0.9999, that would tend towards infinity. But if I said the sum k, which equals 1 to infinity, of 1 divided by k to the 1.00. Okay, so the harmonic series itself, its growth towards infinity is literally a dividing line between convergent series and divergent series. So that's why when we talk about the big theta notation of the harmonic series, and we say, oh, the big theta notation of the harmonic series is it's big theta of the natural log of n, it does tend towards infinity, but it tends towards infinity in like the slowest possible way.